Your turn, Colin, on the hot seat. Talk about GGUF, about the LLMs for the people, not just for enterprises. So I don't know if you want to share like any.
I don't think I have anything. I'll see if I can get one while I go.
Okay, just for example, like let's start about the llama.cpp sort of event or a momentum. Like do you have any sort of background on how it was unfolded? And obviously you started late 2023, but
yeah, so
like,
I
can
was
you tell us?
there towards the end of the initial acceleration. Like I kind of had a little bit of vision on it at the time. Georgie was, hacking away on his MacBook trying to get the recently leaked Llama code running on it, and got something working that seemed to perform reasonably well. And the particularly interesting part about it was that at the time, obviously, the Mac inference engine, that wasn't a thing. There was no way to run language models locally on like a laptop. That just, people weren't doing that yet. And so that was quite the revolution that he was able to figure out how to do that and get it running in a stable way that was, relatively performant and was similar to what was being output by enterprise. Obviously, since then, it has expanded tremendously. Obviously, and from based on what we're here talking about today, quantization was one of those main ones that kind of pushed it forward in the consumer field, at least. And so, being able to quantize the model down to smaller sizes, they had Q40, Q80, things like that, and those represented 4 bits, 8 bits of quantization, so that it could run on load up into significantly smaller GPUs, because that's typically what the issue is with consumer hardware, is that we don't have a lot of RAM. You look at an H100 that's got 80 gigabytes of RAM. That's a huge amount, can load basically anything onto it. But then you look at what they have on the consumer side, even the most expensive one you can buy now, the 5090, like $3,000, $2,000? It's only 32 gigabytes of RAM still. That's like less than half of what you can get on an enterprise card. So it becomes tricky to load, these, particularly, the 70 billion parameter models. It's basically impossible in any other way. And the other thing that GGUF does nicely compared to some other libraries that exist is that it allows for partial offloading. So you can run most of the model on your system RAM, but then have those activations that Elder talked about happen on your graphics card itself. And this still provides a massive acceleration versus just running everything on a CPU. So like for myself, I have many things that I need to run with GGUF, and I'll just leave the entire model on system RAM, but just throwing the calculations onto my 3090, which only has 24 gigabytes of VRAM, it can't do a whole lot. It accelerates, I think, like 2 to 4x the speed of calculations. Wow. So just being able to do something like that to load up massive models without having an enterprise level GPU is definitely where its claim to popularity came from.
You're loading the model in CPU RAM, and you offload the activation or run the activation in your GPU, right?
Exactly. Like the KV all runs there. And so that's where I get my acceleration from, because obviously I can't load particularly large models, but I need to for iMatrix, which we'll probably get into later. Where was it? Oh yeah. So the initial quantization schemes, the blockwise quants that you can see on your screen, they were relatively naive, all things considered. They performed fine. They were surprisingly good, honestly. Like going to Q40 and still maintaining a pretty good amount of quality was probably shocking at the time. But then came the K-quants, which I think are really what make llama CPP. Yeah. So and I think it's probably good to point out at this time, you can load up my image, the IK llama CPP, because this is the I always forget. Iwan Kawrakow.
Kawrakow. Yes, like who's that guy, by the way? Yes, Kawrakow. Ivan. I mean, yes. Like Eldar is like W in Eastern Europe means V. Like Iwan is Ivan. Okay, cool. So yes. Iwan Kawrakow. Who's that guy?
Kawrakow. That makes a lot more sense than what I was pronouncing all this time.
Yes, who the hell is this guy?
I mean, it's still a great question. All I can really for sure say is he is a genius in the field. He does a lot of incredible stuff. He still maintains a fork of his own right now for llama.cpp. That is kind of where it's almost like his testing grounds, where he just commits all these wild things. He's got state-of-the-art quantization available here. But in the past, he worked on llama.cpp directly, and he introduced this concept of k-quants. He introduced I-matrix. He introduced the I-quants, which came after the k-quants. So k-quants was basically, so the way that llama.cpp quantization works is it defines these blocks in order to group weights together to be compressed together and have a shared scaling factor. And that's why we get like better than just straight up quantizing to 4 bits. We are able to share some of the information across multiple weights in order to maintain additional quality. And so k-quants did this even more so. Like it had quantized scaling factors. It had super blocks and regular blocks. Like it's honestly, it's wild to even conceptualize. And then
you're right, man, because I've been reading a lot before writing my blog. By the way, I'm just going to share to the audience the blog that I wrote. So I've been reading in Reddits. I've been reading in GitHub. So he had like an explanation of the perplexity of every type of quantization approach by bit and stuff. And then at the end of his explanation, he said, I should have a documentation around it, but I don't have time. That's literally what he said. So this is how hard, how hard to find like information or like background information about what you're talking about, super blocks and especially the k-quants. I mean, I found out that K means key means. So maybe I'm wrong, but that's apparently what it means. K-quants means key means quants, right? So it's actually a smart bit allocation, right? As you said, it's not like just 1 bit, but like within 1 block or 1 super block, you may have like some weights that are like 4 bits, others full precision, and then others like 6 bits and stuff like that. And then it's a sort of like an average. When you say like key is like a Q4K, it's like an average 4 bits, but it's not totally 4 bits for every weight. Is that correct?
Yeah. So it groups all the weights into so for Q4KM specifically, it groups the weights into blocks of 256 weights. So it starts with that, and then it defines some it defines some minimum values so that you can keep track of what the minimum in that weight block is, some scaling factors, and then it actually quantizes the weights themselves. And then it can use the combination of the scaling factors and the minimums to retrieve similar to the initial weights and maintain the relationship between all of the weights within that block. And so based on so there's the actual weights themselves are 4 bit. Then there's the scaling factors, which are kept at, I believe, 16 bits. Excuse me. And then there's the minimum values, which are 6 bits. And altogether added up over, excuse me, over the 256 weights in the block, you get 4.5 bits per weight effective quantization. And so that's why like the number 4.5, it doesn't sound right. Like how do you quantize to half a bit? Well, it's because it's an average over the entire super block and then over the entire model if it was all done to Q4K.
Right.
Because
So
because Q4K, there is a slightly unfortunate naming here where so Q4K is a type of quantization that's going to 256 weights per block and defining the scaling factor and all that jazz. Q4K_M is a quantization target of an entire modle. So that'll probably end up being, yeah, exactly. It'll be a little bit more than 4.5 bits per weight because some of those weights, some of the layers, some of the weights will be quantized to a slightly higher level because part of it's like they found, you know, the feed forward net down projection. We actually do a huge benefit if every so often we quantize it at a slightly higher rate rather than keeping them all at Q4K. And so that was all done with experimentation. Yes, I should be able to pronounce that name. Sorry, I just noticed the comment.
That's funny. Okay. Yes. Fair enough. Fair enough.
No, you're right. You're right. So there's this unfortunate naming in that sense where Q4KM is something different from Q4K, but it does primarily use Q4K
as an approach.
Exactly. Yeah. So most of the weights within a model will be quantized to Q4K, and then a few of them will be left at different levels because people found over time that it works better to leave some of them at different levels.
And to your point, I just want to maybe like our audience, just for those who don't know, because I didn't know back in the past before writing that blog what scaling factor means. So if like, would you correct me? So as I understand, scaling factor is like when you have a sort of a skewed value in your matrix. And then at some point, like the scaling factor would be something like that all the weights will be sort of multiplied by, so they can have like not a too high or too low value, right? So this is like you're sort of like a mean value of all the weights. Just because you have that scaling factor, you multiply everything by that scaling factor, and then your matrix will be like okay because
it blows it up like to the original range basically.
Got you.
Yeah, it's like a linear mapping. If you imagine like the unquantized weights can be in the range minus 100 to 100, and you want to quantize them to minus 10 to 10. So you're going to be using a factor of 10 just to kind of like, it's like a linear mapping to map it down to a smaller range.
Yeah, exactly that.
It's like you know what? Like I have a music background a bit, so it's like sometimes when the bit rate or the frequencies of you go from WAV to MP3, sometimes some frequencies are not really useful because human being cannot hear it right in a song or a track. So when you compress, at some point they get rid of all those blanks somehow, and they focus on where like in sort of graphic or like temperature picture, was like a thermal view of it. It's like, where is all the concentration? This is where I trim, right? And all the like the blank, I remove it more or less. Is it more or less what it means? Like, would you like sort of draw a parallel between the two? Because when I see that, I'm like, oh, you know what? Like music was like that too, because at some point, like some frequencies on the track are not heard. That means it's not a big deal for a human being if like you remove those frequencies when you compress the track. But maybe I'm divergent here. But
yes and no, in the sense that quantization will reduce noise in general. So you will have fewer of the outliers that would potentially be something like you're talking about in music, where like, you know, you might lose a really high pitch for one part of the song because it just wasn't able to fit in to the envelope of how much you were quantizing it. But I wouldn't say it's necessarily targeting that in a logical sense, at least not for GGUF. There are other ones like, for instance, AWQ and Llama V2, now V3, they will purposely go through and find which weights are more important. So it's like, for instance, if there was a part of the song that had a ton of music in it, like way too much information, but it was kind of important, like it made the song. What these ones will do is that they'll quantize other areas a little bit more to leave this area a bit bigger.
Full
and
precision.
That way, exactly. So that way you can kind of maintain the important section a little bit nicer, while sacrificing the less important sections a little bit more.
Got you. And we have one question from one of the from the audience. Maybe the quantization naming at some point it was confusing for some people, but Q4 means 4 bits. K means k-mean, for example, and then you have the size when you said like how much do you want, and then you have S, which means small, M, correct me if I'm wrong, means medium, and then L means large, and now they have XL, UXL, because these are new, really fresh. I'm used to SML. That's all I knew back in the days, but now like they have UXL, XL. So am I correct? This is more or less how it's...
it's more or less, in terms of like the official ones, there's really only the SM and L. And even at that, only Q3 has an L. Honestly, it's probably at the point where it would be nice if we could go through and rename everything, but it's too late. Like the ship has sailed. It's just happened, and it is what it is. But yeah, so it is confusing in that sense. It's difficult to find the resources. Like I try to do my best to explain it, but it's just hard. It's just they were named when the project was just kind of flying by the seat of its pants, and no one went back and tried to fix it, because why would you?
You bet. Oh, well, all I know is at some point, like the sweet spot for anyone who wants to use more or less small models, quantized models, the Q4KM is like really the sweet spot for people that want to try it for the first time in terms of quality versus size. And performance. That's what I usually use. I rarely go to L. It's mostly M. If depends on how much gigs you have, obviously in your hardware, right? But mostly you can, like, your key M is cool. Q4 key M is like, you can start with that and then see where you can go from there for sure.